The Webb glance is such a long way out that it is catching light that has already been voyaging for over 13 billion years. Yet the universe has been expanding, and thus the light has been stretching as well. For the most distant worlds, we're looking back to just before the Big Bang. The vastness of the universe might appear overwhelming, but every last bit of it started from what we allude to as the singularity. As of now, this is how we apply the Big Bang hypothesis. Anyway, the James Webb Space Telescope, JWST, has revealed significant mysteries concerning the formation and growth of the universe, leaving us dumbfounded. Prestigious physicist Brian Cox has proclaimed that the noteworthy findings of the JWST could actually alter our perception of the entire universe. Join us as we dive into these new heavenly discoveries that promise to change our understanding. The James Webb Space Telescope, named after the recognized NASA administrator James E. Webb, continues to be a marvel of modern galactic investigation. This telescope represents a huge mechanical leap forward from its predecessor, the Hubble Space Telescope. Thanks to a collaboration between the European Space Agency, ESA, NASA, and the Canadian Space Agency, the JWST surpasses the abilities of its herald. It utilizes cutting-edge technology and a design optimized for focusing on the universe in remarkable detail. Unlike Hubble, the JWST conveys sharp images of far-off celestial bodies, working primarily in the infrared range. This unique capability allows it to peer through cosmic dust and capture objects that were previously hidden from our view. With its enormous primary mirror, 6.5 meters wide, and composed of 18 hexagonal segments, the JWST dwarfs Hubble's reflector. It is situated roughly 1.5 million kilometers away from Earth, orbiting around the second Lagrange point, L2. There, it maintains a stable, uninterrupted view of the cosmos. While peering into the farthest corners of the universe, the JWST isn't just exploring light years, it's traveling through time. Its infrared instruments observe celestial objects and events that date back billions of years. Because of the expanding universe, light from these objects is redshifted, shifted from the visible spectrum into the infrared. Fortunately, the JWST can detect this infrared radiation emitted by distant celestial bodies. This empowers scientists to study the birth of stars, the development of galaxies, and the atmospheres of exoplanets. One of its most groundbreaking discoveries involves detecting an incomprehensibly massive collection of galaxies at the very edge of the observable universe. This discovery challenges established theories about cosmic evolution, prompting a re-evaluation of key cosmological assumptions. To better understand how we reach this point, we should take a brief journey through the history of space science. Ancient cultures, like the Greeks and Chinese, laid the groundwork for astronomical knowledge by observing celestial movements. In the 17th century, Isaac Newton set the theoretical framework for space with his laws of motion and gravity. Then, in the early 20th century, astronomer Edwin Hubble made revolutionary discoveries. Far-off nebulae were, in fact, separate galaxies, not just parts of the Milky Way. His eponymous law demonstrated that galaxies farther away are receding, faster, offering the first proof of the universe's expansion. Post-World War II, the space race began, marked by the Soviet Union's Sputnik launch in 1957, the first artificial satellite. Then came Yuri Gagarin's orbital trip in 1961 and the 1969 Apollo 11 moon landing, major milestones in space exploration. Fast forward to 1990, when the Hubble Space Telescope was launched. It delivered stunning clarity and insights into the universe. Its legacy includes capturing the pillars of creation in the Eagle Nebula, a stellar nursery of gas and dust, the Hubble Deep Field, revealing thousands of galaxies in what appeared to be empty space, and the detection of organic molecules in exoplanet atmospheres, hinting at the potential for life beyond Earth. Tracking phenomena like supernova SN 1987A, Hubble shed light on the life cycle of massive stars, cementing its place in modern cosmology. JWST, its successor, builds on those achievements with even more advanced technology. It represents our evolving understanding of the universe's origins, currently explained by the Big Bang theory. Around 13.8 billion years ago, the universe began as a hot, dense singularity. As it expanded and cooled, it gave rise to atoms, stars, galaxies, and the large-scale structures we see today. The Big Bang theory explains the cosmic microwave background radiation, elemental abundances, and large-scale structure of the cosmos. While once challenged by alternative models like the steady-state theory, the discovery of cosmic background radiation in 1965 offered strong confirmation. Later missions like WMAP and COBE, along with technological advancements, further validated the Big Bang. The JWST is equipped with next-generation infrared instruments that allow it to see the oldest light in the universe, light emitted shortly after the Big Bang. This allows it to focus on star-forming regions hidden from optical telescopes. Infrared wavelengths can penetrate cosmic dust, unlike visible light, making JWST ideal for studying cooler objects like exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, their light is stretched, increasing the wavelength, redshift. The JWST detects these redshifted signals, capturing light from the early universe and offering insights into dynamic cosmic events like black hole mergers and new star births, which release primarily infrared radiation. Its ability to detect these hidden signals allows it to explore phenomena invisible to previous telescopes. Complementing optical telescopes like Hubble, the JWST pushes deeper into space and further back in time, expanding our cosmic understanding. The JWST is our window into the earliest stages of cosmic evolution, and it has already revealed findings so astounding they may fundamentally reshape our comprehension of the universe. Re-examination of cosmological models. Re-examination of the whole cosmological simulation of the universe has led to the discovery of enormous masses of galaxies at the outermost boundary of the observable universe. These ancient galaxies existed just a few 100 million years after the cosmic dawn, before the Big Bang. The fact that we are uncertain about how such massive structures developed so early in the universe's history might cause us to reevaluate our understanding of galaxy formation and evolution. Observing early galaxies in the universe is essential for deciphering the mysteries of cosmic origins. The James Webb Space Telescope, JWST, can gain insights into how galaxies, stars, and planetary systems arose and evolved over billions of years. These observations also contribute to broader questions regarding the fundamental character of the universe, including its elements, structure, and the forces that control its evolution. While the Hubble Space Telescope was revolutionary for its time, it had limitations in observing the early universe. Its main restriction was its inability to effectively penetrate cosmic dust or detect the infrared light from ancient galaxies. Hubble relied on visible and ultraviolet light observations, which are often absorbed or scattered by interstellar gas and dust. In contrast, the James Webb Space Telescope represents a significant leap forward in observing galaxies from the universe's infancy. Unlike its predecessors, the JWST can observe celestial objects that came into existence within a few 100 million years after the Big Bang. Using its infrared sensitivity and advanced imaging capabilities, the JWST has uncovered an abundance of ancient galaxies, offering remarkable clarity and detail in understanding the universe's evolutionary history. Preliminary results from JWST observations have stirred waves in well-established models of the universe. The detailed data challenges several aspects of current theories, prompting cosmologists to reconsider foundational guiding principles about the structure and evolution of the cosmos. Discrepancies between observed data and theoretical predictions have sparked intense debate in the scientific community. WST observations have uncovered a greater number of galaxies in the early universe than current models predicted. This suggests a more complex and rapid evolution process than previously believed. Some observed early galaxies appear to have developed far more quickly than conventional models, which forecasted slower growth. The discovery of such unfathomable masses of galaxies challenges the assumed distribution and arrangement of large structures, revealing that the cosmic web is more complex and denser than initially considered. These observations raise fascinating questions and open new avenues for exploration. The existence of large structures in the early universe challenges our earliest models of cosmic structure formation, prompting researchers to refine their theories. For better explanatory power, understanding how these massive structures could grow so quickly after the Big Bang presents a puzzle that demands answers, without violating fundamental principles of cosmology. Significant disparities in the conditions of the early universe, compared to predictions, have emerged. Additionally, new models are being developed. These variations may suggest previously unknown physical processes, unanticipated circumstances, or even unidentified cosmic phenomena. In simple terms, scientists are responding to these surprising results by reconsidering and enhancing our models of the universe. Currently, all we can say is that further exploration is required to incorporate these findings into a more comprehensive understanding of the cosmos. Observations often provide exciting, deep-dive vistas into the universe. Initial investigations can reveal unexpected differences. For example, early observations may show specific arrangements or properties within distant galaxies that become clearer upon closer examination. These studies often reveal fluctuations in structure or evolution, or variations in chemical composition, all of which contribute to the complexity of cosmic phenomena. Spectroscopy, a tool for understanding. The cosmos spectroscopy is a powerful tool for deciphering the properties and history of celestial objects. By examining the light absorbed or emitted by astronomical bodies, spectroscopy provides detailed information regarding temperature, density, chemical composition, and movement. This analysis helps us understand the origins, development, and contributions of celestial bodies to the cosmic tapestry. The JWST has revealed numerous cases where initial observations were later contradicted or refined. For instance, early observations of distant galaxies suggested straightforward structures dominated by light elements like hydrogen and helium, consistent with theoretical expectations. However, spectroscopic analysis using the JWST has revealed differences, such as the presence of heavier elements and compounds previously undetected or misunderstood in the early universe. This challenges conventional views on the early universe's chemical makeup and the mechanisms responsible for element formation and dispersion across vast distances. Similar assumptions about the uniformity of early galaxies have also been overturned. While initial observations suggested a relatively consistent pattern of development and organization, more detailed studies revealed a diverse and complex array of chemical compositions within those galaxies. Transformative power of the JWST. The James Webb Space Telescope continues to redefine our understanding of the cosmos by illuminating previously hidden corners of the universe. One of its most exciting capabilities is the ability to study exoplanets in unprecedented detail. By analyzing the atmospheres of planets orbiting distant stars, the JWST can detect crucial chemical signatures such as water vapor, carbon-based molecules, and organic compounds like methane and carbon dioxide. These findings offer valuable insights into the potential for habitable exoplanets and the conditions that might support life beyond Earth. In addition to exploring distant worlds, the JWST is transforming our understanding of star formation. It can observe the birth of stars in regions cloaked by dense clouds of gas and dust, regions optical telescopes cannot penetrate. With its ability to detect infrared light, the JWST captures the faintest glimmers of newborn stars as they emerge from the darkness. This offers a clearer picture of the processes that lead to star formation and the development of planetary systems. Astronomers are gaining a deeper understanding of how stars like our Sun come into existence and evolve over time.